Hi, everybody. Thank you so much for coming out. I know it's been a long day. We're the last thing probably standing between you guys and a beer or a craps table or a blackjack table. So we really appreciate you guys coming out and spending an hour with us. This talk is called Data Science and Best Practices for Apache Spark on Amazon EMR. My name is Jonathan Fritz. I'm a senior product manager on the Amazon EMR team. And presenting with me is Manjit Chahal, a specialist solutions architect at Amazon Web Services. So real quick, running through just generally what we're going to cover in this talk. A quick overview on why Apache Spark is being adopted really fast for data science, interactive workloads, and those sorts of projects. And then a few interesting features about running Apache Spark on Amazon EMR. We'll go through quickly a few sample architectures that we see customers using Spark on EMR for. Then Manjit will go through best practices for running Spark, and then we'll show you a quick demo with Apache Zeppelin, the new notebook UI that we just launched on EMR, to do a few sample queries. So real quick, how many people here have used Apache Spark before? Okay, great. How many of you guys have used Spark on AWS? So decent amount. And how many of you have used Spark on EMR before? Great. Well, hopefully this will be a quick refresher then. So we see Spark being adopted a lot. We've seen a lot of Hadoop MapReduce jobs. Spark is one of the new engines. And there's really a few reasons why we see Spark being really popular for interactive workloads and iterative workloads. I mean, besides the fact it's a massively parallel system, you add on another node, you can scale out. There's a few things, because Hadoop does that as well. There's a few things Spark does particularly that make it fast. First is it uses directed acyclic graphs instead of, say, just standard MapReduce to plot out query execution. This allows Spark to be more optimized in running queries versus Hadoop MapReduce, where you have to have that same framework for each step of the job. The second thing is Spark minimizes I/O by using RDDs, resilient distributed data sets, that are like basically in-memory data sets to reduce the I/O from going up and back to disk. Versus Hadoop, say for a Hive job, in between every MapReduce job, Hive will write things out to HDFS, or in the shuffle phase, MapReduce will write things back out to local disk. Spark, however, keeps everything, as if it can, in memory, so you can have quick access to data sets, but also if you're running iterative queries when you're doing your analysis, you don't have that I/O overhead. And finally, and Manjit will go a little bit more into this in the best practices, Spark is partitioning aware, so it does everything it can to reduce shuffle, which can have network bottleneck. Hadoop, on the other hand, has shuffle phase in between map and reduce, so it forces that stage to happen. Next, we see Spark being very popular, and as many of you have been using it, you probably use some of these components too. It has a lot of tightly integrated components allowing you to address a variety of different use cases with Spark. At the core, it's the Spark core execution engine. That's generalizable execution engine. But on top of that, there are a bunch of libraries that you can use for things from streaming use cases. If you say have a use case where you need to be able to interact with data coming in very fast versus batch processing, distributed machine learning libraries and Spark ML. Available for you to use, and Spark SQL as well if you want to use a SQL interface. But all of these come tightly packaged in Spark, and you can interoperate between them, and we'll show an example of that a little bit later. Spark speaks your language, so you might feel more comfortable running analysis in a variety of different languages, and Spark, unlike Hadoop, Hadoop has Hive and Pig and some other higher level languages, but they're not as tightly coupled. In Spark, there's native support for Scala, Python, and Java, but also Spark SQL is tightly integrated with a SQL interface, and Spark R, which has just come out, allows you to play with your data in Spark using R as well, and that's available in 1.5 and 1.4. Spark, you can interact with the shell, but also there's a new notebook that's come out over the last year called Apache Zeppelin. We'll show it to you in a demo, but it makes interacting with Spark even easier. You can use the language of your choice, although Spark R isn't supported yet, but to interact with the data and then quickly visualize it, save your queries, and have multiple people collaborating on one notebook as well. So I mean, so you have data in S3 or an HDFS, and you want to get started and use Spark to process it. So what's the next step you might do? So at the core is the Spark DataFrame, which is a distributed collection of data organized in column, and it's an extension of the RDD API. And it has some optimizations as well that make it very performant to interact with. In this case, here's an example. In Zeppelin, there's a default Spark context, but it's very easy to create. You have your files, you just create the data frame, and then it's available for you in kind of a relational format, and you can interact with it in any of those languages that I've showed you on the previous slide. So it's really that simple to get up and get started. You can cache the data frame in memory for even better performance, or you can have it read it in from disk and still get pretty good performance on your queries. Data frames, easy to create. You can create them natively from JSON, Parquet. If you have Hive tables, you can easily translate that into a data frame. Or you can have Spark RDDs already cached in memory, and you can create data frames from those as well. But if you have data in other formats, Spark supports that too. The Spark SQL Data Sources API allows you to connect and load in data from, say, an Elasticsearch cluster or Cassandra. And there are many more libraries that are being developed as well, but it really shows the extensibility of the data frame, being able to bring in data from really whatever source you need to be able to play with it in Spark. Here's just a few sample manipulations. I mean, nothing too complicated here, but once you get the data in the data frame, literally it's just exposed and you can start running queries on it. You can describe fields. You can do whatever you need to do once it's in that format and it's registered with Spark. I brought up before Spark a variety of different libraries that are tightly integrated. One of them was MLlib, which is a library of distributed machine learning algorithms available to use. And once you get data in a data frame, it plays very nicely with those libraries, and you can use the data from that to train machine learning models, generate machine learning models, and test and those sorts of things. So, the Spark languages play very well with those libraries. Same thing with Spark Streaming. You can create data frames in your streaming application, or you could create another Spark context and run ad hoc queries on a stream as long as you have the data cached long enough for you to be able to query it. So if your workload requires you to maybe run batch processes on data that's pretty static, but you need to, say, do a join with something that just came in, that's available for you as well, depending on what you need to use in your analytics workload. Quick example of R. Spark R is available in the latest few releases of Spark. You can access it in the Spark shell. You can create a Spark application that's executing queries with R. And it's got comparable performance, we found, to Python and Scala data frames as well. And hopefully there'll be support in Zeppelin soon for it. And then finally, Spark SQL as well. Once you get your data frame up, you can run more BI-style queries using SQL. If you have a lot of Hive QL, you can create a Hive context and use your Hive QL instead of Spark SQL, because there's some differences in those languages. And it's not one-to-one comparable yet, but we found a lot of success of people porting those over. And then you can connect via a JDBC or ODBC to another BI tool you might have. So, Spark, variety of different language support, built-in support for machine learning. It's very easy to get things into a data frame, and it's fast. And that's why we've seen Spark becoming adopted really quick for interactive workloads where you need queries to return fast, or things that you've been iterative workloads as well. So Amazon EMR, we launched full support for Spark in June, which we were very excited about. We had customers running Spark long before that, installing via Bootstrap action. And there's a few interesting features that we found customers really like when running Spark in EMR. It really boils down to a few high-level points. It's super easy to install and configure Spark on EMR. It's really easy also to add and remove capacity. It's just an API call. Variety of ways to interact and submit work. Different cost structures depending on the nature of your jobs. If they're batch workloads, if you want to use EC2 Spot, which is where you bid on your capacity, you can get up to 90% off your instances. There's a variety of security features, and you can use S3 instead of HDFS as your data layer to dissociate your compute and your storage resources. So Spark, easy to install and configure on EMR, and we're very committed to being close to releasing Spark, the latest version of Spark in EMR, very soon after it's available in the open source. And here's a few examples. We're very quick to launch Spark 1.4.1 after it was released, and Spark 1.5 we actually released on EMR release 1.4.1 last week. And we're going to continue being very close in supporting whatever the latest version is, just because there's fast-moving code base, a lot of new features, a lot of very important bug fixes as well. So it's easy to install. We install Spark on Yarn. We choose Yarn for a variety of reasons. One is you can install a lot of other apps on your EMR cluster as well, and Yarn is a good resource manager for also Hadoop MapReduce and some of the other applications in that stack. So if you want, you can install MapReduce and Spark, so you can use Hive and MapReduce and Spark on the same cluster. It's really up to you when you choose the applications that you want to install. But there's also a few other features in Yarn that are pretty useful. One is just a variety of good schedulers in Yarn. If you want to run a priority schedule or some other things depending on your use case, you can toggle those on and off in the Yarn settings. Yarn also allows you to dynamically allocate executors, and Manjeet will go into a little bit more detail on what that means, but supplies some automation around figuring out the actual resources needed by your Spark job versus you telling Yarn, hey, I need 10 executors. Also, Yarn supports Kerberos authentication if that's required for your use case. So easy to create. You can create a Spark cluster with as many nodes as you need. From the AWS Management Console, that's a quick snapshot of our quick create, but we have a more advanced create if you want to twist more knobs in creating your cluster. We have the support on the AWS command line interface. It's just a create cluster command. There's a variety of commands you can use and script against if you want to easily launch clusters, or you can just use the EMR API directly, and it's really that simple. We configure your Spark cluster with default settings. When you say want an R3 instance, we've done performance testing to know how much default settings for memory allocation we need to give Yarn and things like that, with the goal of just you create a cluster and you can use it immediately without having to tweak all the different settings. And by default, though, we use Spark's default settings for executors, so you will want to change those settings like Spark executor cores, and that'll come up in the best practices on a few ways to think about that. But it really is that easy. We have a configuration parameter. You specify a JSON with all the settings that you want to change, and when you create the cluster, we'll override those settings for you if you'd like. One great thing about running Spark in AWS is a variety of different data stores you can use depending on your use case. And with EMR, we see our customers querying data from a variety of different sources that might be siloed. Amazon DynamoDB, a NoSQL database in Amazon, you can use the EMR Hive connector to pull data out of Dynamo and then run queries using Spark with that. You can connect via JDBC and Spark SQL to Amazon RDS, the relational database service. If you have an Elasticsearch cluster running, you can allow Spark to query that. One really popular use case is using Kinesis or Kafka to stream data into Spark Streaming, and all of that is easily available and configurable in your environment. And then finally, S3. So Amazon EMR has EMRFS, the EMR file system, which is RS3 connector, which is fully usable by Spark. And that allows you to performantly and securely process data in S3 with Spark. You're not copying it into HDFS and then querying it. You're reading it directly and creating an RDD directly from your data layer in S3. But more interestingly, it allows you to decouple your compute and storage. So instead of sizing your Spark cluster, say, for your data that needs to be replicated 3 times in HDFS, you can size your cluster to the amount of memory and compute you need for your job. So in some cases, you can save a lot of money by doing that. Or if you don't need your cluster up, let's say you want to run some investigations on a data set in S3 today. You could go into the office, spin up a cluster, do whatever processing you need to do, and shut the cluster down and stop paying for it. And a cluster comes up within a couple of minutes. So it's very tailored to however you really need to use it. And S3 is designed for 11 nines of durability, low cost, and very, very scalable. So we see a lot of customers using that instead of HDFS as their data store. Running Spark and EMR, there's a variety of ways you can run your Spark workloads. You can create a Spark application and submit it to the EMR step API. And you upload your application to S3, submit some information about it, and the EMR API will, in serial, send those applications up to Spark running on your cluster, run the job, and then typically the output of that job will be pushed back to S3. So that's an easy way if you have, say, a batch job that you want to run after working around figuring out the business logic you want, putting it into production. It's a good way to just run jobs on a regular basis. But if you want to do more ad hoc workloads, you can SSH to the masternode of your cluster and access Spark via the Spark shell in an interactive way, or use Apache Zeppelin now and pull that up in your browser and use Spark for more ad hoc interactive analytics. And finally, there's a few security features which we've seen customers use depending on the requirements around their workloads. For encryption at rest, many customers are using S3 as their data layer. EMRFS supports both Amazon S3 server-side encryption or Amazon S3 client-side encryption, either bringing your own key from an HSM or whatever key vendor you have, or using AWS KMS key management service to store your keys. On the cluster, there's two file systems, local and HDFS. On EMR release 4.1, which was last week, we released the ability to install the component Hadoop KMS, which can supply keys to encrypt HDFS at rest. If you need to encrypt local disk for, say, spills from an executor, you can use just general LUKS encryption using a bootstrap action, which is a script that runs on each node when a node starts up to encrypt those volumes as well. For encryption in flight, traffic from S3 to the EC2 instances that make up your Amazon EMR cluster use SSL. But if you use client-side encryption, they're also encrypted over the wire as well for double protection. On the cluster for inter-node communication, HDFS encryption is done in the client, so the communication between data nodes doesn't need to be encrypted because the actual blocks are already encrypted. And then for certain Spark operations, broadcast and file server, you can enable SSL for those processes, but for the block transfer service, which is used in the Spark Shuffle, does not use SSL yet, and there's a Jira open for that, and hopefully that'll be a new feature in one of the subsequent releases. And then finally, there's just some other general security features that Amazon EMR integrates with if you want to run your Spark clusters very securely. Amazon EMR, you're required to use IAM roles with your cluster, which determine the permissions of both the Amazon EMR service and the EC2 nodes that make up your cluster. There's two different roles that you use. You could enable Kerberos if you'd like, and you can use IAM users to call the Amazon EMR API. From a networking perspective, you can launch in a VPC, and you can also tailor security groups on your cluster. We have default ones that we use, but you can layer whichever settings you want over that. And then finally, if you want to audit who's accessing your Spark cluster via the EMR API, you can use CloudTrail as well. So we have many customers who are running Spark on Amazon EMR. Here's a few examples of some folks who are running it. And really the use cases are a very large range. People running more ad targeting or recommendations engines to security event streaming workloads where they're looking at and predicting interesting things coming out of logs from a security system. These are a few slides that we showed at Spark Summit when we launched Spark in June. One of them is the Washington Post's architecture, and they use a few different Spark clusters to power some of their forecasting and recommendations engines, and then heavily utilize MLlib to run some of these machine learning models. And the thing, though, is that these are productionized workloads. They're running. They're always on. But there was a lot of just ad hoc work to figure out what the business logic was to be able to build it into these production systems. And it was very easy using EMR to spin up new clusters to test, and then moving it over to a production stack. GumGum also uses Spark on EMR to do a variety of workflows. Here, they have an always-on Spark cluster that's working as an interactive dashboard and a forecasting system, allowing BI engineers to go in and play with data in a really fast response time with cached RDDs. But they also use batch Spark clusters to spin up, do some processing, shut down, and then load into Redshift as well for other workloads, and use other systems for just development and test. So it's a really versatile platform, and there's a lot of different things you can do with it. And with that, I'll turn it over to Manjit to talk a little bit more about best practices for Spark.
Thank you. So let's go into the best practices for running Spark on EMR. So let's look into the session, what I'll be covering in the best practices. So starting with which instance types you should pick, and then going deep into the executors, understanding executors, how they work, and then you'll look at the storage layers because how you organize your files matters in your performance, and then tuning of your jobs. So how do you boost the performance? And finally, we'll go with the demo and showing how you can use Apache Zeppelin notebook on EMR. So going first into what does Spark need? Spark needs a lot of memory. And then when you're doing some kind of machine learning process, you need CPU, and then you need network. So these three things are required. So if these three things combined together form an instance. So you need to select an instance with a proper set of memory, a good networking, and a good CPU based on the workload. And so once you have selected the instances, you need to scale out. So Spark offers horizontal scaling. So the more the instances you add, you can scale up your processing. So let's look at the type of the workloads the workloads and the resources you need for it. So for like machine learning, it's more CPU intensive. You need a machine with CPU intensive. If you're doing an ETL processing job, look for a machine which has more of I/O resources. So these are the different instance types which you can see in the EMR. So first is the general instances. They are M1 and M3 family. The CPU instances, C1, C3, and then we have another class of memory-intensive machines, and then the disk I/O. The disk I/O machines would have huge storage. So each machine has a different, which can be used for good workload. So a general machine can be used for a batch processing. CPU type machines can be used for a machine learning. And when you're doing many interactive analysis, so in Spark, you need to cache all the data in memory. So you need a machine with enough memory, and that's why you'll go with the memory-intensive machines there. And if you're using a large HDFS, go with the disk I/O family. So now you have the instances you need. Now let's go deep into the executors, what executors are. So look at a simple Spark program. The two things are there. You have a Spark driver, and then you have a Spark executor. Now as a user, when you submit a job, it goes to the cluster, and then on all the executors is where your job is running. And once all the executors complete the results, they send it back to your user, the driver. So this is where all the action is happening. All the processing happens in executor. So let's go deep into an executor, what happens there and how it is structured. And when you go into that, you will always have so when you're doing applications, you always get into a trouble like, okay, how many executors do I need for this application? And how many CPU cores should I give to this executor? That's always a problem. And best thing is to understand by means of an example. So the example let's consider here is, let's say we pick a family of machines R3, and for our example, we'll go with machine R34XL, which has 16 cores and 122 GB of RAM, 220 GB of SSD drive, and a high networking. So using the AWS CLI, you can create this cluster using the steps here. So look into this. Here I'm selecting R34XL, and I'm picking 6 instances of that. So 1 master and 5 core. And you see the EC2 attribute key name, my key, that's the key which you provide. So now once your cluster is up and running, now you're configuring, okay, how many machines do I need? Now let's consider into how do you select the number of cores? So you leave 1 core for the OS and the other activities, and then for a good optimal performance, you leave 4 to 5 cores per executor. So in each executor is where you have the tasks, And when you're doing a processing, let's say you're reading and writing data from HDFS, each task has a thread. So when you read data and write data to HDFS, you have 4 to 5 threads running and writing there. So it gives you good performance. And this 4 to 5 threads it's been derived like after multiple iterations, optimizations, and see, I found that 4 to 5 threads makes a good sense. So considering a 4 to 5 number of cores per executor, so this is simple formula you can use to set number of executors needed per node. So you have one machine, R34XL. In that machine, you can run 3 executors. And how that comes is total numbers of the core on the machine is 16. We're leaving away 1 core for the OS, and then 5, that's the number of tasks per executor. So that's the number of the last slide I discussed. You can leave 4 to 5. So in this case, we're selecting 5. So we get a round off number to 3 executors per instance. So looking at this, now we have 6 machines totally, 3 executors per node. So totally we'll go with 18, and we'll leave -1. That is because when you're submitting a job in a cluster mode, your application, it runs in one of the executors there. So you leave 1 for that. So totally you'll be selecting 17 executors for your cluster. So now you have decided, okay, how many executors I need. Now the next thing comes on how much memory is required for my processing. So Spark on EMR runs in a yarn mode. So in yarn, you have the main thing, yarn containers. This is where the process, the application runs. So when you submit a job, it goes, the containers are launched, and within a container space is where your application runs. So the size of the container is decided by the configuration, yarn node manager, resource memory MB. And that configuration you can set in the file yarn site XML. For our example, we are using R34XL that has a default of 116 GB. So that's the size of the maximum size of the container on the machine. Now, in this container is where your Spark job will be executing. That's the container space, I would say. So inside a Spark job, in a Spark executor, you have one thing called memory overhead, executor's memory overhead, where VM overheads, internal strings, they are cached there. And that is I would say it's like an executor memory into 0.10. That's the derivation for it. And that configuration you can set in Spark default.conf. Next, other space is for Spark executor memory, the rest of the, so this is where the amount of memory is used by the executor. And you can set that in the Spark executor memory configuration using in the file Spark default. So you have, in this memory space, you have 2 things. One is your shuffle memory fraction, the fraction of the Java heap space, which is used for aggregations and co-groups. So when you're doing an aggregation in your Spark job, this space is used. And next, other space is the storage. So these 2 are the memory fractions which you consider. And for storage, the default is 0.6. So now you have a shuffle memory fraction, you have a storage memory fraction. These are inside a Spark executor memory. So looking at our example, so executor memory for this yarn container, how much should it reside? The maximum container size by number of executors per node. So for this example here, we have 116 GB as your container size, and on one instance, we are launching 3 executors. So by 3, that rounds out to 38 GB. So that's your executor memory. Next, we're considering the memory overhead. And memory overhead, as discussed, is your executor memory into 0.10. That's roughly is 3.8 GB. And so overall, what you'll have 38 GB, and you subtract that 3.8, and that rounds up to 34 GB. So that's the space where your data will be playing around, moving in that. So that's 34 GB. So now you derive this number. And you can set this configuration in Spark default.conf. Or like when you're running a job, how you can set it by passing executor 17, number of executors score is 5, and executor memory of 34 GB. So for this cluster, when you're running application, the optimal configuration, so best utilization will be this. So now you have a cluster up and running. Since it's yarn, you can run multiple applications in this. You can have idle resources, and when you're done with execution, you have some idle space left. And you're always query like, do I need, how many number of executors I need? For that, let's, in Spark 1.3 version onwards, dynamic allocation was released. So dynamic allocation lets you forget about the setting number of executors. And what that is, when you're not doing the processing, it removes the idle executors. And when your application requires more processing power, it requests those. So you can idly scale up your applications and down based on the demand. So in the dynamic allocation, scaling up the executors, what it allows you to do. So your jobs complete much faster because now you have more executors at your jobs application, and then you're using the idle resources on the cluster. So let's say, for example, I launched a 100-node cluster, and I'm processing, and other applications are finished now. So I have extra resources left. I can use those if I have set the dynamic allocation. Next is on this, once you have decided, okay, my job is running, and then how many executors are needed. So Spark decides that, okay, I can exponentially allocate more number of executors for your job. So you can configure dynamic allocation using these parameters. The first two in this dynamic allocation enabled, you set that flag to true, and shuffle service enabled to true. So these two are must. The remaining others in this are optional. You can configure them, and those are the minimum number of executors you need for this application, the maximum executors you can go for, then initial number of executors required, and execute idle time. If an executor has been idle for, in this case, 60 seconds, release it. So using these parameters, you can actually enable dynamic allocation in the Spark. And dynamic allocation is available only on Yarn for now. So now you know which instance types you have picked, you know how to configure the number of CPUs, how much memory is required. Now let's jump into the storage. Storage, when you go in, first thing is always use compressions. Compress data when you're storing it on Amazon S3, what it provides you, idly you are saving space. So if a 10 GB file now compressed goes up, let's say 5-6 GB. So you reduce cost on the storage. And when you're doing an application and it's reading data and writing data from Amazon S3, you're transferring it over the network. So instead of transferring, let's say 10 GB, you're transferring only 5 GB, so you're actually saving time there. And it reduces the bandwidth there. And next is it speeds up your job because compression. So these are the different compression types. So there's gzip, LZO, snappy. And looking at the performance of these, you'll know like, okay, which one should I pick? So some compression algorithms are fast and offer less space on the total size. And some are efficient but slower. Efficient, I would say they're eating a lot of CPU cycles and they're trying much time is spent in compressing the data. So they're slow in there. And next is you have splittable compressions. And some files are not. So there's so many choices on which compression file should I pick. Which one should I take, which should not. So if you're time sensitive, you can go with the faster compressions. It's always a better choice there. But if you have a large amount of data, and then you use space efficient compressions. If you really don't care which compression, just go pick gzip. So now you know which storage. Now how do you boost the performance of your job? How do you make it faster? So first thing you'll go into is data serialization. So when in your job, let's say these two things here, one is both are Spark executors, and when a data is moved from one node to another, from the memory it goes to the disk, and then that's serialization there. And when it goes back it's transferred over the network to the other node and it's pushed back in the memory. So when you're doing a caching or shuffling, a data serialization, deserialization happens. In Spark, the default serializer is Java serializer. There's a faster one called Cairo serializer that is 10 times faster than the default Java serializer. It is not as default when you launch a cluster because it does not support all the serializer types. And when you're doing let's say you write a scalar code and write the application, that application should be registered in advance with the Cairo serialization. And you can enable this configuration to use Cairo serializer using configuration.set Spark serializer and enable that. One thing is Spark doesn't like to shuffle because it's expensive. You're taking data from one machine, pushing it to other machine, and it requires a lot of disk I/O. You're spending cycles there. You're wasting time in the time which can be used for processing is spent on the disk I/O, data serialization. And more shuffle means more network I/O. Your data is moving here and there and spilling to disk. And as there's more shuffle, more operations, it increases the garbage collection. And when garbage collection happens, your job sadly goes slow. So avoid shuffling. And how do you avoid shuffling? Let's go into that. So for example, when you're doing a group by aggregations, you can go with something like aggregate by key instead of writing your own aggregator. So this is an optimized aggregator. An example of that is, let's say you have an RDD called my RDD, and you can call that for, so I have a mapper key K and V, so you can do an aggregation on those. This is an example line for how you can use that. And apply filter on the data earlier in the stage. So when you're processing huge amounts of data and you're not going to actually touch everything, try to filter it ahead in the stages. Next is on parallelism and partitions. Spark is a distributed parallel cluster, I would say. When you're running a process, the more parallelism, it's much better for your jobs. And the configuration when you launch a cluster is set in spark default.conf, and the parameter is spark default parallelism. So when you run a job in your Spark executor, you have the RDDs. The RDDs are further broken out. They have multiple partitions. And the partitions has a correlation to the parallelism. So let's say you have a really big RDD, and it has, let's say, 100 partitions on it. Spark knows that it has 100 partitions, but how do you know it has 100 partitions? So there's a function you can use get number of partitions that gives you that. So when you do an operation between two RDDs, so the first RDD and the second RDD, there's an operation happening on that. And when the job runs in an executor, it uses those threads, the CPU threads, to actually do the processing there. So for short case will be if you have more than 10K tasks, it's good to coalesce. And if you're not using all the slots on your cluster, repartitioning can increase the parallelism. And you can leave 2 to 3 tasks per CPU core on your cluster. Ideally, what that boils down to is for one CPU core, have 2 or 3 tasks there. And this configuration, you can set in spark default.conf. Persistence. So Spark has started with the concept of RDDs. And RDD is where the data is kept in the memory, caching. So when you're doing a processing, you're storing the data in memory. And when you want to, let's say in a machine learning case, you're reiterating over the data, you're processing it many times. So it's good to cache there, and cache it and persist it in memory. So the methods you can use for a cache or persist. So for example, I'm doing a data warehousing query, and I need to do some analysis. So instead of fetching the data every time from the disk, bringing it in memory, doing a query, that's a little intensive. So for the first time when you're fetching data, bring it in memory, cache it there. Now once it is cached, any other iterations you're doing, let's say I'm doing a first group by, everything is in memory, gets it. And for the further iterations, the data is fetched from the memory. So it's much faster for you. Now, which RDD which will pick and what type of storage level do you use for? So for small RDDs, you can go with the storage layer memory only. And for big RDDs which cannot fit in the memory, you go with something memory only SerDes. It is CPU intensive because excess data is being spilled to the disk there. First thing, don't spill to disk, I would say. And if to have a really fault tolerant cluster and your application should not stop in between, I would recommend you go with replicated storage for faster recovery. So you can go with 2x replication, 3x replication of your memory objects. So let's go into the demo, and I'll show you how you can run Zeppelin on Spark. Yeah. Is this visible? So I have an EMR cluster running Zeppelin, and I have created a notebook Spark on EMR. So in this example you see here, we are using the data set in Parquet format, which is present in this S3 bucket, and we create a data frame called flight data frame. And once this data is read from the S3 location, this data is around 70 GB in size. Once it is fetched, we'll register the table as a temporary, and then we'll print the schema. So it's very simple. So it's a simple type. You can type everything in. So I will just select this piece and run it. So it's fetching the data, and it has printed this, and it took. So this Parquet file has information on the flights data set. And it's only for domestic US flights. So it has fields like year, quarter, month, and many fields, and where the flights are taking off from, where the flights are landing, the delay time, taxi time. So the next one is, let's do a group by on the unique carriers on that. So it fetches the data, runs a query, and gives you the result on the screen here. So it's more interactive. When you're doing an analysis, right now let's say if you're going with the shell mode, you're doing a Spark submit and doing processing, it's not very friendly, I would say. So having a browser, you can just log in there, you can share the notebooks. Zeppelin is really cool in that way. So for this example, this gives you unique flight carriers. And the .show operation gives only the top 20 records. And Zeppelin, in that terminal, you can write a Scala code, or you can even do a SQL query. So looking at the example here, we have registered this table as a flight. So it is cached as a temporary table. And so doing a count on this table, select count star as total records from the flights. So it has 162 million records. And the entire count star took 3 seconds here. And similarly, doing other type of analysis on this. So you can put a bar chart, you can put pie charts, different charts in this. So this one shows you the top 10 airports with the most departures since 2000. And similarly, the top 10 busy airports in December of 2015. So it's easier to interact. So Atlanta, so many flights have taken off from there. And these are busy airports. And similarly on this, let's say I want to find all the flights leaving Seattle between 2004 and 2014. This is a simple SQL query, which I have on the table. It's a simple count and group by. So this one runs, and it plots the results here. Okay, done. Similarly, you can have the configuration on number of flights leaving Seattle between 2004 and 2014. This gives you the analysis, and you can easily do analysis on your data sets in a very quick manner, interactive, save it, and you don't have to reprocess data again because this thing is saved here. That's it. So we're good?
Yeah. I guess, thanks. Thanks, everybody, for coming out. We're happy to take some questions. We'll be down here, and we'd love to chat with you guys, learn more about your use case, and answer any more questions. So thanks. Have a good rest of the conference and a good night.
Thank you.